The decommissioning of large synchronous generators and at the same time the increasing penetration of converter interface distributed generation within the power system is already presenting a number of challenges such as reduced and variable inertia. In the near future, the increasing deployment of flexible resources such as controllable loads or electric vehicle charging infrastructures at the extremities of the network are expected to bring in further challenges, but at the same time they do present an opportunity for decentralized control. And this is evident by the transition of distribution network operators into distribution system operators. Within the ELECTRA project, working with our European partners, we have proposed a novel decentralized control architecture for the future power system called the Web of Cells. Web of Cells enables collaborative operation of a number of smaller regions of the power system called cells. These cells rely on local observables for more effective local actions to minimize global system disturbance impact. A number of voltage and frequency control algorithms have been developed for the Web of Cells architecture. And here today in the Dynamics Power Systems Laboratory, we will be experimentally demonstrating the systems level validation of one such control. We will begin by my colleagues describing the experimental setup.
At the Dynamic Power System Laboratory, a harmonized procedure for performing control hardware-in-the-loop and power hardware-in-the-loop is used for validating the performance of different control algorithms and different control structures, such as the Web of Cells. In this case, for testing the controllers developed for the Web of Cells concept, a multi-cell power system has been developed. This power system has been divided into two different sections. One of the sections that comprises multiple cells is emulated with the use of the real-time digital simulator, while the other section that comprises a couple of cells is emulated by using the components in our laboratory. These components are such power converters, induction machines, synchronous generator, or different load components. The simulated model and the laboratory equipment are interfaced with the use of a 90 kVA back-to-back power converter. Also, measurements from the laboratory are required to couple the dynamics of the simulation and the hardware in order to perform an accurate simulation. Different domains are required for performing the experiments. In this case, we will be showcasing the power domain, the control domain, communications domain, and finally, visualization and decision support.
My name is Paulius Dombrovskis. I'm a researcher here at the University of Strathclyde and I work on telecommunications for power system applications. Power hardware have raw measurements. Those measurements then are processed locally and they need to be transported to a control location, like a control center, or in the case of the ELECTRA project, the Web of Cells cell controller. Here at the university, we've built a communications emulation platform which allows us to realistically represent that data transfer and apply all the necessary delays, all the necessary performance implications. This communications emulations provides us with confidence in our results and helps in validating the performance of the distributed Web of Cells controls architecture.
So my name is Anthony Flowder James and I'm a PhD student here at the University of Strathclyde. The Web of Cells frequency control algorithm has been implemented within the distributed control platform, which is situated within the Dynamic Power Systems Laboratory. So the controllers receive measurements from PMUs and simulations. The emulated comm system then transmits the set points for the controllers.
My name is Minjiang Chen, a research assistant at the University of Strathclyde. My research focuses on multi-agent system design, distributed intelligent control, and decision support design. Within the ELECTRA project, my role is to design visualization and decision support to deliver Web of Cell concept in the lab. Using this visualization, it allows users to visualize the experiment. Also, the decision support system can prioritize the solution, and the user can select from the visualization. And the decision support system can automatically take the optimal solutions if there are no response from the user at a certain time. After meeting, myself and my colleagues will take this whole procedure to achieve the practical experiment, and we're going to show the real experiment now.
Having had the experimental setup described by my colleagues, now we will move on to a live demo of balanced restoration control. What we will be doing over here first is do a frequency event by means of a generation loss. We will emulate a generation loss that represents 1 gigawatt of generation loss. And then there will be another event that will be a load loss, which represents 1 gigawatt of load loss. So as it begins, as you can see, the frequency has started to deviate, and this has been detected by the controller that has been developed, and the restoration has already begun. But what is important to notice is it has not only helped in restoring the frequency, but also improved the frequency another. And as we can see, the frequency has been restored within 30 seconds, which is quite fast. When you consider the conventional control, it can take about 10 minutes for the frequency to be restored. The frequency is already back to its nominal value. We will go for another event, which is a load loss. So as can be seen again from the screen, the frequency has deviated from 50 Hertz. It's rising. It has been detected by the controllers. The controller is activated, and now the frequency has already been, it's being restored, and within, let's say, 10 seconds, the frequency will be restored. So this slide over here basically tries to give a comparison between the proposed control and the conventional control. And as you can see over here, that the conventional control takes about 100 seconds for the frequency to restore to its nominal value, whereas with the proposed control, with fast detection of the event, the frequency has been restored within 40 seconds. And again, for the load loss, as you can observe, the same thing. The conventional controller takes about 100 seconds to restore the frequency, whereas the balanced restoration control is able to restore the frequency within 40 seconds. What is also to be noted is that the balanced restoration control can have a bit of an overshoot, but it is well within the trumpet curves that have been defined by ENSO-E, which represents a very good control for the future power system.